Let me share my screen with you. So you should all see it now. What you see on the left side here is a pulse of light that moves through a glass fiber, right? You have all heard of glass fibers. You know, the internet is now supposed to come out of a glass fiber. What happens there is the pulses of light move through a piece of glass, and this is what you see here, and it happens at the speed of light. So down here you actually see a time scale, and you see that it goes from 0 to about 8 or 9 nanoseconds. 1 nanosecond is a billionth of a second, so it's a really short time, and we have slowed it down for you here by a factor of 500 million. Making this movie took, of course, a really, really long time in order to get the technology to this point. And so I would really like to take 1 minute to just introduce the other members of SEEK. SEEK stands for CC, where C stands for the speed of light. So we see the speed of light, we see light move at the speed of light. And the other members are Ena de Dios Rodriguez, who is an artist, who is a photographer and a filmmaker. And you should all check out her website because it's really wonderful work. Then there's Philipp Haslinger, who is an assistant professor at the Technical University here in Vienna. He is one of the world's experts in using quantum physics to measure the tiniest forces that you could think of. Then there's Brennan Klopfer, who is a grad student at Stanford, and I had the great pleasure to work with him for 4.5 years, and he really has many, many talents. So it was a great honor. And myself, as Fotini said, I'm an assistant professor at the University of Vienna, where I'm working on new tools for microscopy. But with that, let me go on to the next slide. And basically, Fotini and Lise, they asked me to answer the questions that you can see here, namely what drives you, what questions do you ask yourself, how do you learn, and how do you collaborate? And to be honest with you, these are not questions that I'm used to. You know, people ask me, how does this or that kind of microscopy work? Which laser should we use? Things like that, but they never ask me what drives me. So it's hard for me to really answer this, which is why I thought that I could just go the other way and discuss with you what was driving me in the last years. And you know, going back, I started to study physics, and my humble youthful goal was, of course, to learn how it all works. I soon got very disappointed because I realized that I could never learn it all. But I still enjoy the journey, and it's those tiny questions that you can ask that I find super interesting and super hard to answer that really keep me going in science. And the first such question was one that is about 80, 90 years old now, and it is about the double slit. Who of you has heard of the double slit or matter waves? Clemens has, he already mentioned it in his talk. Let me give you a very brief introduction to it. Okay, so assume you have a source of electrons. So you have electrons coming out here, and then you have a wall, and in this wall you have a slit. Then, of course, many of these electrons here, they will be blocked by this wall. But some will also make it through here. And so if you have a screen here, they will all land in this region behind this slit here. Now, you know, that we all kind of get quite easily, but what happens if we put another slit here? So now we have 2 slits. Now, what I would have expected as a naive student is I thought there would just be 2 of these bumps, but this is not what happens. Actually, what happens is you get an interference pattern, and you get a bump here, and a bump here, and a bump here, and maybe a tiny bump here, and a tiny bump here. It's totally weird, right? Why would that happen? If I take 2 slits instead of 1, why don't I get 2 peaks? Why do I get 5 peaks? You can explain this using quantum physics. It all works out nicely. You just have to attribute a wave behavior to the electron. And this is weird because then if we look at our screen, we will not see the wave as a whole, but we will see one particle length here, another one here, another one here, another one here, then another two here. And in this way, this interference pattern kind of builds up with time. And that was just something that I could not wrap my head around clearly. And so I decided to do a master thesis on this topic, and more specifically on the topic of why does this work with electrons and not, for example, with tennis balls or with golf balls. Because actually in quantum physics, there's nothing that prevents this from working with a tennis ball, but we never see this with a tennis ball. Okay, so after about 4 or 5 years of work, this is the built with friends of mine, of course. And what we did here is that we had a molecular beam source back here. And then this molecular beam would travel through a steel chamber that is evacuated. And then in the midst of it, there would be a tiny nano grating, so lots of tiny slits, just as we have seen them on the last slide. And then we would deposit this molecular beam on a screen, on a screen back here. And the reason why I'm bringing this up, I mean, this is work that is now more than 10 years old, is that on the one hand, this is where I met Philip, because Philip had his lab, you know, just 2 meters to the right here, and he built a setup that looks more or less like mine, but that actually was a lot cooler than mine. And via Philip, I also met Ena, because they were in the same circle of friends. And as Clement said, this experiment here is also the reason why he and I met. Because the outcome of this, what we would saw on this screen, is what you see on the video that's playing now. And that is the one that Clement maybe let me make a pause here. Every tiny little dot here that you see is a single molecule that was flying through our chamber onto the screen. None of them knew of all of the others, and yet for some reason they form this pattern. But this was more or less one of the outcomes of my PhD thesis. Of course, there was more physics to it, but this was the one that I thought was really cool and that I put on YouTube, and then Clemens found it and found our group. So I enjoyed that quite a bit, but after 5 years of doing fundamental physics work, I wanted to do something more applied. And I've been looking for topics where this waviness of matter can actually be used. And it can be used, for example, in electron microscopy. Electron microscopy is this great tool where you send an electron beam on your sample and you see what the transmitted beam looks like. And this can be used these days to unravel the atomic structure of proteins. So really of the molecular machinery that is inside of our body, right? When Clement said that there's plenty of room at the bottom, in biology, this room is actually filled with amazing tools. So this technique won the Nobel Prize in 2017, but there's still a problem to it, namely that you can only take one single picture, because while you look at the structure that you want to study, your beam destroys it, right? So you can only look at it once, and of course you would love to be looking at it many times so that you could make a movie and that you could see how this protein machinery actually works, right? So the topic of my postdoc, which was then in the US, was, are there any tricks from quantum physics that we could use to get more information per interaction, more information per interaction between an electron and the sample? So it's again a super simple question to ask, but one that is not so easy to answer. we came up with a scheme, and I'm very happy that a new kind of electron microscope is now being built according to the plans that we have made. That's on the one hand, to me, you know, it's an honor and it's super cool. On the other hand, it's super frustrating because it takes really long and it's just not easy. But I'm hopeful that at some point within the next 3 or 4 years, it will actually work. So this was another 4 years of my work, if you wish, but it was not just work. There were also some good times, especially also because Na and Philip, they also both moved to the States. And so we also met there, and we, you know, danced and had dinners and discussed. And at one of those dinners, we discussed what we could do with the instrumentation that we have in our labs, and whether there was any way how we could use it for the arts, right? And then we realized that we had the tools in the lab to image light move at the speed of light. And that's, for me, that was kind of crazy, because Philip and I, we have been working with lasers for 6 or 7 years at this point, but we have never seen light move, right? So of course, immediately the next day we went back to the lab and started working. And, you know, at first, of course, nothing works out, but then you spend a few days and weeks on it. And then in the end, you start making movies like this one here, where you can see how a light pulse moves across a stuffed bird. You know, the light pulse first scatters back from the front of the bird, and then it passes the bird, and then after some time, a nanosecond later, it reaches a wall where the shadow is formed. So now you see the shadow of the bird. So you see light move. You also see that the image of the object itself doesn't happen at the same time as the image of the shadow, simply because, you know, light moves at a finite speed, namely at the speed of light, 3 times 10 to the 8 meters per second. It's extremely fast. Yeah, but this is what we started working on. And there's our website, seekphotography.com, where you can see many more of those. But let me maybe sum up the questions that Fortini and Lise asked me. One is, what drives you? And in thinking about, you know, what I've done in the past, I think it's on the one hand, the things that I don't know, like I really want to know things. And on the other hand, it's trying to make things happen that have never been made happen. So just doing things that have never been done just has some kind of excitement, just creates some kind of excitement for me that I really, really like. So this is what drives me. What I'm curious about right now is, as you might have heard, the molecular machinery that is inside of our body. That is, for me, a huge step from doing physics to now working at the Vienna Biocenter, which is one of the biggest biohubs in the EU. It's a big step for me, but I really love it. And the third question that you asked was, what is your mode of learning? How do you learn, and how do you collaborate with others? And I think the mode of learning for me is that I really, I work quite a lot on these topics. As you have seen, it always starts out with a very simple question to ask, but then you invest 4 or 5 years in it. And this is really my mode of learning, that I immerse myself in these topics. And my mode of collaboration, there I would say that it's one of the really greatest privileges of my job, that I often meet people who are extremely creative and extremely intelligent. And some of those are, you know, Clemens and and I'm super happy that they had the same interests as I had. And then you start working on some topic, and you can be pretty sure that cool things will come out of it. And all of a sudden you have the band 5/8 Linearen in your lab with laser goggles and immersed in laser light. Yeah, thanks.